So this type of matrix, this is a diagonal matrix because we only have entries on the main diagonal. So there was actually a question in the homework about what would happen if we took a diagonal matrix and multiplied it by itself. So we could jump straight to the conclusion of that homework question and say, because that's a diagonal matrix, a to the fourth should look like 2 to the fourth, 0, 0, negative 3 to the fourth. So we could jump straight to that answer, meaning, let's see, 2 to the fourth, that's 16. And 3 to the fourth is 81, and that negative 1 times negative 1 times negative 1 times negative 1 is going to loop us back around to a positive number, and that would be 81. Now, to get there the slower way, we can actually multiply this matrix by itself 4 times. So let's start by computing a squared, which would be the same thing as taking that matrix A and multiplying it by itself. I know that these are both 2 by 2 matrices. Since their inner dimensions match, I know we're okay to multiply, and those outer dimensions will give us the overall size of the answer. So my answer is going to be a 2 by 2. And when I come in here to do our multiplication, I know that to get the entry in row 1, column 1, I take row 1 times column 1. So I'll end up with 2 times 2 plus 0 times 0. To get my entry in row 1, column 2, I take row 1 times column 2. So I'd have 0 times, or sorry, 0 plus 0. So I still maintain that 0 in the corner. For this entry in row 2, column 1, I'll have row 2 times column 1. So that's 0 times 2 plus 0 times negative 3. We keep that 0. And lastly, I've got row 2, column 2. So row 2 times column 2, 0. And then negative 3 times negative 3 is going to give me a positive 9. And then you could repeat 2 more times. But like I said, we know that this is a squared. We know that a was diagonal, which means we can jump straight to the answer to say a to the fourth, because it's a diagonal matrix, is 2 to the fourth, 0, 0, negative 3 to the fourth. 4, negative 6. 6, negative 9, 4, negative 6. So the first thing that I'm going to do is compute b squared. So I'm going to take b and multiply it by itself. 6, negative 9, 4, negative 6. So we'll find b squared first. Again, it's 2 by 2 times a 2 by 2. So I know that our answer is going to be another 2 by 2. 6 times, so to get the entry in row 1, column 1, I'm going to do row 1 times column 1. So 6 times 6 is 36. 4 times 9 is also 36. So I've got a positive 36 plus a negative 36, and I get 0. Now to get the entry in row 1, column 2, I need row 1 times column 2. So now I've got 6 times negative 9, so it's negative 53. And negative 9 times negative 6 would be a positive 53, so I've got negative 53 times plus positive 53, and I get 0 also. Now I'm at row 2, column 1. Row 2, column 1. I've got 4 times 6, so that's 24, and a negative 24. I get 0. And row 2, column 2. Row 2, column 2, I've got negative 36 plus a positive 36, and this is also 0. Which means this matrix has a special name, and it is nilpotent. And now computing b cubed is going to be really easy, because if this is the answer for b squared, then if I take b squared and I multiply it by another matrix, all of the entries are going to have to be 0. So b cubed will also be the 0 matrix. Questions about this guy? So we want a times b to equal I2. So again, we're going to practice our multiplication. We're just going to drag that k along with us. And to compute my row 1, column 1 entry, oh, just to back up for a second, this is 2 by 2. This is also 2 by 2. Those inner dimensions match, so we're able to do the multiplication, and these outer dimensions give me the size of the answer. So to get my value in my entry into row 1, column 1, I need row 1 times column 1. So 2 times 2, that's 4, and -1 times 3, that's a -3, so 4 minus 3, I get 1. Well, that's good, because I'm trying to make A times B equal to the identity matrix, if we can. So far, so good. I also need to get a 0 here and a 0 here, so let's make sure we do. So to get that row 1, column 2 entry, I need row 1 times column 2, so that's 2 times -1, that's -2, and then plus a 2, I indeed get 0. I also need to get a 0 here if it's going to be equal to my I2 matrix. So now I'm in row 2, column 1. Row 2, column 1. So I'd have 2 times k plus -6. So I'll just write that as 2k minus 6. Just for completeness, this last entry for row 2, column 2 has to be a 1. So let's just double check that. So row 2, column 2, row 2, column 2. So it's going to be -k plus 4. So if this answer is going to match this answer, then that means that 2k minus 6 would have to be equal to 0, and -k plus 4 will have to be equal to 1. So these two have to give us exactly the same solution. Otherwise, we would say there is no such k to make this true. Well, this, I think we can see that if I move the 6 over, divide by 2, k would have to be equal to 3. And if I come over here, this says -k would be equal to -3. So k would be equal to 3. And yes, that's the value of k that will make A times B equal to I2. And to get this population after 1 month, so x sub 1, y sub 1, z sub 1, I'm going to get that by taking our Leslie matrix and multiplying it by the populations we have, the population distribution we have right now, 0, 0, 18. So we're going to do some quick matrix multiplication. So let's check our dimensions. So right now, this is a 3 by 3 matrix, and I'm about to multiply it by a 3 by 1 column vector. The inner dimensions match, so we know that we're able to do the multiplication, And the outside dimensions are going to give my answer. It should be a 3 by 1 as an answer. So to get the entry in row 1, column 1, I need row 1 times column 1. So I have 0 times 0 plus 0 times 0 plus 6 times 18. So a little quick calculator action. 6 times 18, I get 108. To get my entry in row 2, column 1, I'm doing row 2 times column 1. So I'd have 0 plus 0 plus some more 0. And to get my entry in row 3, column 1, I need row 3 times column 1, so I'd have 0 plus 0 plus some more 0. Now, if we think about this biologically, that says we started off with 8 adult beetles, and after one breeding cycle, which I'm saying is a month, after one breeding cycle, there are 108 brand new baby little beetles. There are no juvenile beetles and no adults. So all those adults have died off. We have no juvenile beetles yet, but we do have 108 babies. So now to project that forward one more month, I'm going to take these values and they're going to become my new inputs. So I'm going to erase these difference equations. So to get my distribution after 2 months, we're going to take that same Leslie matrix, 0, 0, 6, 1/2, 0, 0, 0, 1/3, 0. But now the matrix or the distribution we're going to multiply by is 108, 0, 0. Again, I have a 3 by 3 times a 3 by 1. Those inner dimensions are going to match, and the outside result is that my answer should be a 3 by 1. So I'm taking row 1 times column 1 to get that first entry. So I'd have 0, 0, 0. To get my row 2, column 1, I'm going to take 1/2 of 108, which should be 54, plus 0 plus 0. And then I'd have 0 plus 0 plus some more 0. And we could keep doing this over and over again, and we will develop a technique to be able to do that by the end of section 8. We've got cattle on a large ranch, and they're divided into 3 age classes. We've got calves, yearlings, and adults. So just to get a diagram going, I'm going to say that we've got calves, yearlings, and adults. And we know that a calf survives the first year with a probability of 0.7. So that means my calves are growing into yearlings with a probability of 0.7. And then 80% of our yearlings survive to become adults. We also know that the probability that an adult female will survive a given year is 0.9. So that means adults are going to feed back into being adults at a rate of 0.9. And we know that an adult female produces a single calf each year. So our adult females are going to feed back into our calves 1 per year. And because the problem doesn't state anything about yearlings being reproductively viable, that our yearlings are not going to feed back into our calf population. So if I take this and I were to write this as a system of difference equations, So we'd have our C sub t plus 1, our Y sub t plus 1, and our A sub t plus 1. Now for our calves, that's only getting fed into by our adults. So I'd have 1 times our adults. Our yearlings are only getting fed into from our calves. So I'd have 0.7 C sub t. And our adults are getting fed into from 2 places. From our yearlings, so we'd have 80% of our yearlings surviving to become adults, and 90% of our adults living for 1 more year. So that's what our system of difference equations would look like. If we go to put that into a matrix, so again, I think about these rows as telling me our calves, yearlings, and adults for the next year. And then the top, this is where those values are coming from. Are they coming from the calves? Are they coming from the yearlings? Or are they coming from the adults? So for the calves, calves are not feeding back into calves, so that's 0. Yearlings are not becoming calves, so that's also 0, but our adults are producing, on average, 1 calf. For our yearlings, I know that from the calf category, that's going to be a 0.7 because 70% of our calves grow up to be yearlings, but our yearlings don't get to stay yearlings, and adults don't get to regress in age and somehow get younger. Now for our adults, we don't have an influx from calves straight to adults because they've got to grow up. Our calves have to become yearlings and then adults. Our yearlings are becoming adults at a rate of 80%, meaning 80% of them are surviving to adulthood. And then our adults are feeding back into remaining adults at a rate of 90%.